recording. Okay, now I start. It's great pleasure to have Aninda Sinha from Bangalore. He's going to tell us about the relative entropy in scattering and its S-matrix bootstrap. Please.
Thank you very much, Satoshi, and I'm very happy to be virtually in Shanghai. So I'm going to tell you about relative entropy in scattering and the S-matrix bootstrap. So just to make sure that everything works. So I'm pretty sure everybody can hear me, and I'm loud and clear.
Yes, I can hear you. Yeah.
Very good. And assuming I'm audible, I decided that I should take some liberty and define what an on-shell listener is and what an off-shell listener is. So I hope you'll be asking me questions during the talk, and you won't fall asleep. Anyhow, and what I'm going to talk about is how relative entropy, I'll define what relative entropy means in case you do not know what it is. It behaves in 2-to-2 scattering. So it's a quantum information theoretic measure. And you can ask, why would you be studying this in this scattering context? For starters, you may want to know how to distinguish density matrices in a scattering process, or maybe you have two different theories and you want to see how these two theories compare when you're trying to explain some scattering data. So that may be the reason why you might be interested in studying relative entropy. So relative entropy, of course, is something that has been studied in other contexts. So Janet is there in the audience, and she has worked extensively on relative entropy in holography, and there are some beautiful results from that area. Another reason, and this was one of the main motivations why we began looking at this, is because of the reincarnation of the S-matrix bootstrap. So there is a conformal bootstrap that has led to very, very interesting results, and it's still a very, very active area of research. But the S-matrix bootstrap also was rebooted in a sense a few years back. And I'll tell you a bit about the history of the S-matrix bootstrap. The conformal bootstrap historically was developed after the S-matrix bootstrap. And I'll introduce whatever I need as we proceed. Now, bootstrap gives us an allowed space of S-matrices. So for instance, in this figure, I hope you can see my pointer. In this figure, there is some y-axis and some x-axis. And this blue region is some allowed spaces of S-matrices, which describes this particular process of pi plus, pi minus. These are pions, charged pions going to pi plus and pi minus. And in principle, you get a huge allowed spaces of S-matrices. This red cross here, I'll explain it as we go along, is actually where the one-loop chiral perturbation theory lives. And these green regions are interesting spaces of S-matrices. I will explain what these are as we go along. But one question that you might be interested in is, how do you distinguish a theory that lives here from another theory that lives, say, on the lower boundary? So this is like a river. This looks like a river. So I will sometimes call this the river of S-matrices. And I will also explain how this was obtained. I'll explain to you what these S2 and S0s are. These are basically Adler zeros. But you want to distinguish two different S-matrices. And the question is, what would you do to distinguish them? So let me just briefly recall some essential features of the CFT bootstrap. So the CFT bootstrap is way more developed than the S-matrix bootstrap. I should say the new version of the CFT bootstrap is way more well developed than the new version of the S-matrix bootstrap. And so let me just recall something about the CFT bootstrap numerics so that it will help you compare at least the two sides of the story. So the CFT bootstrap, there is an analytic side and a numerical side. So from the numerical side, these are the kind of things that you would encounter. So you would encounter spaces of allowed CFTs. So for example, in this plot, you have a y-axis that is the conformal dimension of the leading scalar operator that appears in the OPE, the operator product expansion of two of the fundamental fields. And on the y-axis, you have the conformal dimension of the fundamental field. So here it is denoted by phi. So in the context of the Ising model, you can think of this as the sigma field. So this space is there, what you would get in 3 dimensions. So for example, if you looked at the case where n was equal to 1, you would get the famous 3-dimensional Ising model. And one common feature in all these plots is that there is some peculiar thing that is happening. So there is some kink, there is some bend in these allowed regions. So anything below these lines is allowed for that particular theory. In principle, I mean, in practice, of course, you would try to bootstrap with more correlators and you'll get smaller regions. But one interesting thing that was observed quite early on is that if you are in below 4 dimensions, so in fact, you could also be in 3.99 dimensions. You could be in a fractional dimension as well. And you did the similar analysis to ask what values of this delta S and delta phi are allowed by the bootstrap equations, you would get some constrained region. And the boundary of this constrained region would have these very interesting features. So for example, the 3-dimensional Ising model, whose scaling dimensions we would know from other sources. So for example, you would know it from Monte Carlo, or you would know it from the epsilon expansion, or some other means. The 3-dimensional Ising model appears to live precisely at the kink. And this actually, this feature continues for any other n. So the O2 is also a famous universality class for it. Is the super example falls into this. The 3-dimensional Ising model, water falls into the 3-dimensional Ising universality class. So these are all very interesting features, and you would ask, okay, so if we did something similar in the S-matrix case, so in the S-matrix case, you have a massive quantum field theory, you're scattering massive particles. It's not really a conformal fixed point. You have less symmetries. So you would try to see, can we generate some interesting plot like this, where we have constraints, we can rule out parameter spaces. So that's basically one of the ideas that you would want to try out initially. And the S-matrix bootstrap, what I'm going to describe, basically leads to similar looking plots. So so S2 and S0 are parameter spaces. I will explain what these Adler zeros mean later on, but you can think of them as analogs of these conformal dimensions in some very loose sense. I'll make that clear later on. And you get in this allowed region, you see that a large chunk, the white region here, would be things that are ruled out. You cannot have an S-matrix that is compatible with unitarity and crossing symmetry that lives in the white space, and so on. This P and L are basically what would be called the peninsula and the lake. I will tell you how exactly these were derived later on as the talk progresses. And as I mentioned, this red cross here is where the one-loop chiral perturbation theory lives. So I will also review a little bit about chiral perturbation theory as I need it. Okay. And I will discuss some interesting results from the S-matrix bootstrap, which makes indirect use or direct use of inequalities motivated by relative entropy considerations. And you will see how these considerations actually gives rise to this kind of a plot. And these inequalities that are motivated through this relative entropy considerations can be thought of constraining these interesting spaces of S-matrices. So, okay, so this, what I'm going to discuss is based on a recent paper that appeared in June. This was written with Anjishnu Bose, Parthiv Haldar, Prithvish Sinha. So Prithvish Sinha is no relative of mine, but and Shashwat Tiwari. So Anjishnu, Prithvish, and Shashwat, they were basically doing their master's thesis with me. Anjishnu and Shashwat, they were also my undergraduate students. So we have been at this S-matrix bootstrap for close to 2 years now. And Parthiv Haldar is my graduate student. All of them are extremely smart. And in addition, we had 50 cores of computing power. And this will be of some relevance towards the end of the talk. So what kind of computing power you would actually need. So 50 cores would be roughly, I don't know, if you have got a nice workstation, maybe 3 of those, but they don't work in parallel, so they are sort of disconnected, so you don't use the full power of the workstation. Okay, so let's begin. So let me tell you a bit about entanglement in 2-to-2 scattering. So this is a usual picture that you would see in any introductory course in quantum field theory. This is two particles, A and B, in the center of mass frame. I will assume that these are massive particles. Throughout, I'll be assuming that all the particles are massive, and in fact, I won't have anything to say if one of the exchanged particles is massless. So we are only assuming massive quantum field theory. So in the center of mass frame, you have an incoming and outgoing particle, or incoming particles, and then they scatter and they become C and D. So A and B are incoming particles, C and D are outgoing particles. This is a 2-to-2 scattering. Of course, more generally, you would have A and B scattering, and then it could be any, it could be 2-to-3, 2-to-4, whatever. The angle that A makes with D is conventionally called theta. And this actually plays, this can be written, this theta can be written in terms of the kinematic variables. So the kinematic variables in the scattering process in the center of mass frame are the Mandelstam variables. So they are called S and T. The convention, I'm going to use some convention. S is minus P1 plus P2 square, and T is minus P1 plus P3 square. The angle, this theta, can be written in terms of these kinematic variables in the following way. Cos of theta is 1 plus 2t over s minus 4m square. And so as you can see that there are physical regions for the scattering. So the physical region would correspond to when you have s bigger than 4m square. So the denominator here is positive. But cos theta has to lie between minus 1 and 1. So for that to happen, t has to be less than 0. So you can define these physical regions. There are these physical regions in each of these variables. So there are 3 variables, s, t, and u. But there is a constraint that relates s, t, and u. So s plus t plus u is equal to 4m squared. And so 2 of them are independent. And you can choose any 2. Conventionally, s and t are chosen. So you can write your incoming state. So this is some notation just to mention what's going on. So A and B are the incoming state, C and D are the final states. And you describe the final state as the S-matrix, the some S-matrix operator, S operator acting on the initial state. So this operator S is unitary. The norm of F has to be preserved. So SS dagger is 1. Now, if I'm restricting to just 2-to-2 scattering, I would require a projector. In particular, I would require a projector if I wanted to consider particles that are at a precise angle theta. So Q of theta is some projector which actually projects onto a particular angle. So the density matrix for the final state can be written in this way. So if you were tracing out the particle B, you would do something like this. So that will give you for you a reduced density matrix. Is that clear? Are there any questions?
Yes.
Okay. So there is a bit of algebra. It's quite straightforward, and I should tell you that entanglement in scattering, we want the way that we are the concept of the reduced density matrix was considered earlier by these gentlemen here. Now, the thing that they did not do and which we introduced is to have this projector, because we have in mind a detector that is sitting at a particular angle. So it makes sense to consider these projectors in place, and you will see the role that these projectors have eventually. Now, from the reduced density matrix, you can calculate the entanglement entropy. So the entanglement entropy is the von Neumann entropy of the reduced density matrix. And as you can see, it has got 2 interesting pieces. The first piece is log of k squared. So k squared is just it's the center of mass 3 momentum magnitude square times the spatial volume V divided by 2 pi, and T here is not the temperature, it's actually the time. So these are actually both infinities. So V is the 3-dimensional delta function evaluated at 0, and T is the 1-dimensional delta function evaluated at 0. So this comes from the algebra. You would expect these infinities to show up. And so this is the divergent piece. And then you have this more interesting piece, which would be a finite piece. So this is very similar to what you would expect from a probability distribution. So you would expect to see P log P from a probability distribution. And rather than being a probability distribution, this curly P actually is a probability density. So what that means is that curly P, let me just show you this formula. So this is actually this projector. This gx is a function that has got support only at a particular angle. So x here is cos theta. So x, whenever I have x in my slides, it stands for cos theta. So g of x would be something that has got support at the angle x. You can think mentally of there being a Gaussian function which has got support peaking at, say, at x. This m is the matrix element, so this is mod square. It's a function of s and t. I have traded, instead of t, I'm using x. So it's normalized in a certain way, and as you can verify, curly P satisfies the condition that when you integrate this between -1 and 1, you get 1. But there is no reason why this is actually less than 1. So in that sense, this can be thought of as a probability density and not as a probability distribution. Okay, so just to, again, make sure that everybody is familiar, so this curly P is going to appear again. It will involve the matrix element, mod square. You can trade off this mod square for the differential, elastic differential cross-section as well. The only thing that is new here is this support functions. Okay. So that was the entanglement entropy. So this one is divergent, as I said. And just reminded, this is matrix element square, and g of x is the support at a particular angle. Okay. Now, what is relative entropy? So relative entropy is a measure that allows us to distinguish two density matrices. It is defined in this way. It is conventionally denoted by D. In classical information theory, this is also called the Kullback-Leibler divergence. And it enables us to distinguish two density matrices, rho 1 and rho 2. So you just require two density matrices, and you can define, using those, you can construct this, this quantity D. So it is just the trace of rho 1 log rho 1 minus rho 1 log rho 2. So that's how it is defined. So rho 1 and rho 2 are just two density matrices. You could think of them in a couple of different ways. So you can think of rho 1 to be the density matrix which describes scattering at a particular angle, say x1, and rho 2 to be the density matrix that describes scattering at, say, angle x2. Or you could also think of rho 1 as that coming from some theory that you postulate. So for example, suppose you are studying some scattering, but you want to see whether you can describe it using chiral perturbation theory, or maybe you want to see if you can describe it using some version of the Veneziano formula. And you want to distinguish these two different possibilities. So the second is what is called hypothesis testing. So you want to test whether your hypothesis is correct or not. And relative entropy gives you a measure to do that. A good place to learn from learn about relative entropy, there are at least quite a few references, but I could recommend the 2018 review, Mini Introduction to Information Theory by Edward Wheaton. So the importance of relative entropy, as I was telling you, is that it enables us to distinguish density matrices. And the distinguishability is characterized by 2 to the power of minus n times d. So d is this relative entropy. And n is the number of measurements or trials that you need to do to be able to say for certain whether you can distinguish the two, say you have two theories, or you want to see whether you can distinguish what is happening at two different angles. So n would be the number of measurements that you need to do that. So if you have d to be very large, then the number of measurements that you need to reach a certain tolerance would be small. So that's roughly the idea here, that the largeness of d tells you that the number of measurements that you actually need to do is going to be inversely related to the largeness of D. Okay. So just to continue, we have some math. So relative entropy, one of the good, nice mathematical features is that these infinities that we saw in entanglement entropy have canceled out. And you have this very nice object. So this is an integral over these probability densities. Now, unlike the entanglement entropy where you had P times log P, you will now have two of these probability densities. So the formula takes on a very simple, nice form. Is P at G1, so this will be support at, say, angle X1, and P of G2 would be support at angle X2. So this is what you would get for the relative entropy expression. Now it's a very straightforward exercise, and I would, those of you who are not familiar with relative entropy, I would suggest that you try to show that relative entropy is positive. All that you need to know is that this is a density, so it integrates to 1. And you require to know something about the properties of the log function. And that is it. And you can actually show that this is going to be greater than or equal to 0. And I just wanted to again emphasize that ρ1 and ρ2 would correspond to scattering at 2 different angles, but it could also be that you're sitting at the same angle, you're sitting with the detector at the same angle, and you have different theories. So is the premise clear? Are there any questions?
Yes, can I ask a very, very stupid question? If you
Yes.
swap ρ1 and ρ2, is it easy to show that this positivity?
Yes, again, it's the same thing. But what you are asking is whether it's not symmetric under the interchange of ρ1 and ρ2. Yeah.
I see.
But it's 1 and 2 are just labels. So what you're asking is actually whether it's a metric in the usual sense of the metric that it is symmetric. It is not.
Okay.
But of course, since 1 and 2 are labels, if you swap 1 and 2, you will still get the same properties.
Okay, thanks.
Yeah, there was somebody else asking. Yeah. Can you speak up? I cannot hear you.
Yan, I think your voice is too low, too small. Huh? I'm sorry, Yan, I cannot hear you. Or if you have a question, can you type in the chat? I think, unfortunately, I cannot hear you. So can you type in the chat?
I think we can't hear you. It's too soft, or we can't hear you.
Please go ahead. I will ask later.
Yeah, that I heard. Okay. Yeah. So if you could type in, I can answer you at the end.
Please type your question.
Yeah, so Jan said that he's going to ask it later. So let me just continue.
So please go on.
Yeah.
Please go on.
Yeah. So as I was saying, that let's consider this case where you have support functions, and we can model the support function to be some Gaussian support. So in some limit where the width goes to 0, you get a delta function. So this is the properly normalized Gaussian function which does that. And when you do that, you can actually have a nice series expansion in terms of the width. So this is like expanding in the detector resolution if you want. So x1 and x2 are the 2 different angles, and x1 minus x2, and it doesn't make any difference whether it's x2 minus x1 or x1 minus x2, because it will be quadratic in the story that I'm going to say. So x1 minus x2 is delta x. Sigma was the detector resolution or the width of the Gaussian. And you can expand in a power series in sigma, and also assuming the delta x is small. So there are two things that are small here. Sigma, we are going to assume that it is tiny, and so it goes to 0. and delta x is also small. So we are in a regime where delta x square by 4 sigma is quite big. So this is the leading order term. And that kind of makes sense because you do not expect to be able to distinguish these two angles if your resolution wasn't sufficiently small enough. So that is why you expect this quantity to be big. And you can expand this function, this thing that I wrote here, in this power series. So the first term, as you can see, does not have, except for this delta x square, which is the difference between the two angles and which you can hold fixed. It does not really depend on where the scattering is happening. So long as x1 and x2, they are held, the difference is held fixed, x1 minus x2 is fixed. It does not really matter where the scattering is happening. So this is like the hard sphere scattering. So I'll call this the hard sphere part. And the other thing to note about this part is that it does not depend on the matrix element. So in some sense, this is in some loose sense, you can think of it as the classical part. The interesting thing starts happening from the second term. And that is why I am going to give it a name. I'm going to call it D subscript Q. And loosely, you can think of this as a quantum part of the relative entropy if you want. And the reason is because this part actually involves the matrix element, unlike the first part. So D, of course, is positive because this dominates, and then sigma is positive, delta x square is positive, so D is positive. This is the leading part. But the question is, what is dq? dq is the thing that actually involves the matrix element. It involves the matrix element, the second derivative of the matrix element square.
I missed something stupid.
Yes.
Is sigma, can I understand sigma as some kind of regularization or?
So sigma going to 0 would actually give rise to the delta function. So sigma, you can think of the resolution of the detector.
Okay, okay. Right, so
okay, yeah. Okay. So the second part is a very interesting part. The second part actually has, as I said, it depends on the matrix element. It involves the second derivative, and the second derivative is being evaluated at x equal to x1. As I said, they are close by angles, so that's why it's a Taylor series expansion, so x equal to x1. And the final feature to take note of is that this part does not depend on sigma. So in that sense, this part is independent of the resolution of the detector, so long as the resolution is small. So this part is kind of interesting. The other thing that you should keep in mind is that it involves the second derivative of the log of the matrix element. And if you do not like to think in terms of the matrix element, you can mentally replace this as the elastic differential cross section. So it involves the second derivative of the elastic differential cross section. It involves the second derivative with respect to the angle. So there are two variables. S is a variable, but there is no derivative here. What is happening is at the level of the angle. So you can ask a lot of interesting questions so far as this is concerned. You can ask whether this is positive. You can ask if this is positive, why it is positive, what is the significance. You can also study various limits of this very interesting thing. You can take S to infinity and ask what's happening there.
Sorry, what is the data for row 2?
Which one? Sorry, row 2. Okay, so row 2 is just the density matrix which has support at angle x2. So here cos theta is x. So this would be a different angle. So that's what gives you row 2. Is that clear? So here, for example, so here, for example, row 2 would be what contributes this probability density PG2. So this would involve a G that has got support at x equal to x2. Is that clear?
Yeah. Sorry, I was trying to repeat the question I want to ask. So I guess you're computing entanglement entropy in the momentum space in the beginning, right?
Yes. Yes, that's right.
Okay. Are these density distribution normalized?
Yes, they are normalized. So integral of PG between -1 and 1 is 1.
Okay.
And also the rho is also properly normalized. So in fact, the normalization ultimately cancels out in relative entropy, but it's all properly normalized. That is something that you have to do. Yeah.
Okay, thank you.
Okay, so any other questions? So this second guy is going to play an important role for part of my talk. So we should be sure that we appreciate or understand what's going on here. Okay, so let's consider. So this I have called a name. So I'm going to focus and I'm going to show you some plots for this DQ. So this is the uninteresting part, and this is the interesting part. So the first one is phi4 at one loop. So you open Peskin and Schroeder. It has got the formulas for 2 scattering at one loop. You can use that, and you can easily compute quite straightforwardly what this DQ is. And it's kind of interesting because, of course, that formula, since it's at one loop, it will have interesting cuts, and you have to do it correctly. So when you do that, and so of course we are working perturbatively. So you're working perturbatively in the coupling. So this is lambda phi4. So lambda phi4 takes on this interesting behavior. So the thing to take note of is that it is symmetric around the origin. That's kind of because it's identical particles. But it is also that it takes on the lowest value. So these are plots at various values of S. So it takes on lowest value at x1 when the angle is, so cos theta is 0. So this is sort of transverse. And it takes on the highest value when cos theta is 1. And of course, you can numerically do it for any value of S that you want. But in the largest limit, you can also do things analytically. So you can take the formula that is there in Peskin and Schroeder, and you can expand. And you can find a nice form for DQ. The formula for DQ, the thing to remember is that apart from this sign of the coupling, so what we are usually taught is that lambda has to be positive, otherwise the vacuum is not going to be stable. Everything else is positive in this quantity. And of course, it also increases, it blows up as x1 approaches 1. So this is the analytic form when S is much, much bigger than 4m squared. This is what gives rise to the dotted line. And of course, you can play this game for other theories as well. So phi4, of course, is, yes, carry on. Yeah.
What does it mean by blowing up?
So x1 at x1 equal to 1, there's a pole here.
Oh, right. Is there any interpretation of what that blowing up? Oh.
Yeah. So just bear with me, and maybe you can you can ask me. So this is in the high energy limit. So this is basic. Yeah. So this is you will see. So it's roughly speaking, when you have very large energies, then in some loose sense you can think of scattering to be massless. So this arises because of some approximate dipole. Yeah.
There's a question in the chat box, so I'll just say it anyway. It says any term proportional to log sigma don't arise.
Log sigma? No, we don't see any term proportional to log sigma. That is that's a good question. I mean, we were of course assuming that delta x is small and sigma is small, and we're doing a Taylor expansion. So there is no logarithmic singularity in that sense. Yeah. Okay. Okay. Yeah. So bear in mind this increasing behavior. Okay, and this will play a kind of an important role. It's a big deal. So just so what is happening here? So let's just spend 30 seconds in trying to state this blowing up in different words. So this blowing up is happening when cos theta goes to 1. The formula for cos theta was 1 plus 2t divided by s minus 4m squared. So this blowing up is happening when t goes to 0. Okay. So here what we are considering is the large S fixed t and small behavior of this function. So this large S fixed t behavior is what is called the Regge element. So this is going to play a role later on. So this was 5.4. So let's consider string theory, because some of us have been trained in string theory. Both Janet and my supervisor invented superstring theory. So we kind of morally owe it to ourselves to investigate what is happening for string theory. So this is, you open Polchinski, volume 2, and then you look at the formula for the 2-to-2 scattering of 2 dilatons going to 2 dilatons. So let's focus on scalars. I mean, whatever I say has a generalization to external spins as well, but it can be done. The formulas are there in our paper. So you just take the tree level. So this is string theory at tree level, and you plot it. Of course, you have to you compute the relative entropy using that formula, and you plot it fixing some S. So here I have chosen some random. So here I've chosen units where 4 alpha prime is string length squared, that's equal to 1. And I've chosen S to be 0.01, to mimic some low energy behavior of the amplitude. And I've also fixed the angular separation to be 0.02. So this is cos theta 1 minus cos theta 2 is equal to 0.02. And again, I've chosen the resolution to be some number. It's something that you can easily do. So here, the blue line corresponds to the relative entropy, this dq. So dq is the blue line. And you can do a sort of low energy expansion of the string amplitude. This is just, will give you the standard supergravity result. The leading order answer is going to be 1 over SGU. So you can take that and you can just work out this dq, and you will get this, which is, again, this is actually positive, and it has the same feature that it actually rises as x1 goes to 1, and it kind of rises in a similar manner. So here also this function was 1 plus x1 whole square divided by 1 minus x1 square. Here also it's 1 plus x1 square divided by 1 minus x1 square. The difference is that here we are considering a low energy expansion, and here we considered a high energy expansion. Now, what happens is that because the string tree level answer has various other poles corresponding to the tower of higher spin massive states, if you kept increasing the energy, you would start seeing oscillations. And in fact, you see vigorous oscillations if you did the similar plot at some very high value of S. But anyway, the takeaway point here is that it has a kind of a similar kind of behavior as 5.4 at high energies. It looks similar. So this was blue. Blue was the relative entropy. Red is in fact the entanglement entropy that I've plotted, and I've subtracted off the infinite part. So the infinite part was this log v by t. I told you that there is this divergent part. So I've just focused on the second part. Okay. So this was string theory at tree level. The thing to remember is this behavior in terms of the angle. Now let's consider a very famous theory, which is called chiral perturbation theory. Let's consider chiral perturbation theory at one loop. And why I'm doing that is because it's an effective field theory. It describes low energy hadron physics. In particular, it will describe for me later on in a bit what happens in pion scattering. In this particular case, you again plot dq as a function of the angle. You will see that for some low energies, it has this rising behavior, but eventually, if I just consider a very large S in these formulas are all available in the literature. So chiral perturbation theory at one loop, it's readily available in the literature if you do a Google search. I mean, the famous review, there are famous reviews by Gasser and Leutwiler and so on. I mean, of course, it was introduced by Weinberg long time back. but it's an effective field theory, so you have to do work. And you'll see that eventually you'll start getting in kind of an opposite behavior. It's not the rising behavior that we saw in the other case. And this is not to spoil the generality of this rising behavior, because effective field theory is not supposed to make sense at very high energies. In fact, chiral perturbation theory is supposed to be sensible only below a certain energy scale, roughly 500 MeV or so. So that's what it is. That's what this relative entropy behaves like. Okay, so what do we do with it? So of course, I said something about the high energy behavior, and I found some interesting angular dependence. So can we sort of understand this? So one of the main results that happened due to axiomatic quantum field theory in the 1960s was these high energy bounds. So people make certain assumptions. They make certain assumptions about analyticity, about polynomial boundedness, the fact that in the complex plane, the amplitude is polynomially bounded. And they reached, so polynomial boundedness, this criteria is sort of proxy for locality. So you want a local quantum field theory. And they reached various interesting bounds. So Andre Martin and collaborators, Andre Martin has done very important work in these high energy bounds. So there's a very famous bound called the Froissart-Martin bound. It was first done by Froissart, and Martin made it very rigorous. You can put a bound on the elastic differential cross-section, and it has this particular form that this matrix element square mod square at very large S and fixed S, fixed angle, is less than some function of S, and this function is not important. It is known. F of S is known. You can look at these papers and they'll tell you what f of s is, but f of s ultimately cancels out in what we are doing. And there is some 1 minus x squared to power p. When you use this, you immediately get this high energy bound. And this, in fact, is what explains these kind of angular dependences. So the phi-4 and low energy string theory respect this kind of a form. Now, why are we doing low energy string theory? Why are we comparing low energy string theory? Roughly speaking, loosely speaking, is because if the energies were very high, then basically you can think that the masses are irrelevant. So in some sense, you're dealing with massless particles. So you can derive high energy bounds. Now, what do you do with it? So the first thing to realize is that this bound is telling us that this quantity TQ has a rising behavior and it is positive. So, and that's the only thing that I'm going to need in what I'm going to tell you next. And I'm doing extremely badly with time, so bear with me. So one thing about bounds. So what does it tell you in the context of what we learned about relative entropy? So relative entropy was, it told us that if we wanted some understanding of some phenomena up to some tolerance, fixed tolerance, then if you have d to be less than equal to something, then that corresponds to the number of measurements being bigger than something. So in other words, at high energies, because of the existence of such bounds, we have to work much harder to be able to distinguish density matrices. So that's one consequence of this, these bounds. Now, using all this technology and background, we can actually study something very interesting about Regge trajectories. So what are Regge trajectories? So here is a lightning review. So if you open the particle data group handbook, this is a nice exercise. It's an interesting exercise because as string theorists, you finally feel you're doing something useful, maybe. You can actually look at the resonances for light mesons. And you can see that you can write down the location of the poles. You can ask me what these poles mean in the context of this matrix later on. But you can write them down. The imaginary part actually tells you something about the lifetime. So in fact, the higher resonances, sigma, rho, F2, and so on, which correspond to higher spins, rising spins, they have some finite lifetime, which is way smaller. Lifetime is way smaller than what the pions do. So in that sense, in the context of this table, the pions can be considered to be stable because they are very close to the real axis. But the interesting thing, and this has been known for a very long time, is that if you plot a graph of the spin versus m square, this is famously called the Chew-Froschi plot, and Jeffrey Chew and Froschi first plotted them in 1962. They didn't have so much data. I think they had 3 points or something like that on their plots, but nonetheless, you get these Regge trajectories. You have almost linear behavior. Almost is a very important word. And this is this almost linearity is what gave rise to string theory, because when the Veneziano model was an attempt to find something which had this Regge behavior and satisfied crossing. The real thing is slightly more interesting. So you don't have completely linear behavior. You actually have some curvature. So it actually does not follow a completely linear trajectory. And this is supported by experiments, that it is almost linear, but not quite. You require to have t squared. The important thing is that it is known, or at least there is overwhelming evidence, that alpha 2 has to be positive. And this is something that we can study using whatever we have talked so far. So in the Regge limit, when s is going to infinity and fixed t, and this is slightly different from fixed angle, but it is, we can do something interesting stitching behavior. Your amplitude, the magnitude of the amplitude can be written like this. There is a beta of t that is sitting in front, that also you can take into account. We did that in our paper. You can look at it there. But morally, it behaves like this. This alpha t, this tells you what the Regge trajectory is. And if you calculate this quantity dq, so this left-hand side is dq, it actually becomes proportional to alpha 2. And that's quite important. That is why the second derivative, the form that we were working with, involves the second derivative of the amplitude. Now, it is very difficult to extract information about alpha 2 in most things most physical quantities, because these guys overwhelm it, alpha 2. So experiment tells that it is positive. So this quantity dq, then we learn that it is actually sensitive to the nonlinearity of the Regge trajectories. By the way, this is a nice review. You can learn more about the nonlinearity of Regge trajectories from this review, this paper. So can we argue why alpha 2 is positive? And we kind of want to make a model independent argument. The argument is as follows. So recall that the high energy bound, which is the fixed angle largest bound, was that this was positive. So our arguments run as follows. So we saw, using these elastic differential cross-section bounds, that this dq should be positive as you approach 1. And it's very simple then, that if this is positive, then if you wanted to stitch up these two behaviors, so this is at fixed t, so this is more at the forward limit. If you wanted to stitch up this behavior with whatever is happening at fixed angles, then this alpha 2 had better be positive. Otherwise, you'll have some discontinuous behavior. So this is an argument, or this is to motivate why alpha 2 should be positive. Is that clear? Is there any question before I go on to the next part, which is going to be a lightning review? So I think I'll take 15 minutes if I may. Satoshi?
Sure. Please go ahead.
Yeah.
You can have 15 more minutes.
Yes, thank you. Okay. So are there any questions about this?
Just wondering.
This argument? Yes.
If you improve the relative entropy to something like neutral information, can you delete this hard sphere divergence?
It's an excellent question. It's an excellent question. It is worth looking into. In fact, that will be great. So one thing that you might want to do is to have 3 density matrices and maybe write down something like what you said, or even consider the strong subadditivity. I think that'll be very nice to actually study, because I think using this, you can also ask what kind of tests you can put particle physics data to, and verify whether it satisfies strong subadditivity. I mean, you can ask all these kinds of questions, but it's a very good question. We've been thinking quite extensively how to get rid of the hard sphere part.
Okay, thank you.
Sorry, I have a question.
Yes.
So the S-matrix is supposed to have some branch cuts and singularities.
Yes.
So does the the relative entropy.
Yes, yes.
So how does it affect the properties of the
Yeah.
entropy?
So what happens is, and this is something that I did not have time to show, is say suppose phi 4, when you dial S, the cut happens from 4. So if you stare a little bit at the plot, you will first see that these curves first begin to decrease. They decrease up to 4 and then start increasing. Okay, so that is one effect of the existence of a cut at S equal to 4. So these kind of behaviors will happen when you have cuts.
Oh, okay. Thank you.
Yeah. Okay. So this was something about the Regge behavior. So let me just tell you in the next 15 minutes or so what to do with QFTs. So this is a lightning review of S-matrix bootstrap. So S-matrix bootstrap was a very old idea. So basically, some of the founding fathers of quantum field theory or quantum mechanics, they were not very happy with the way that quantum field theory was progressing, because at that point of time, you had these infinities, and these infinities were being sort of swept under the rug. So historically, the concept of S-matrix was introduced by John Wheeler in 1937. Now, very interestingly, in 1943, in the middle of the war, Heisenberg wrote a very important paper highlighting the importance of using the S-matrix. And then, of course, it lay dormant for a while. In the 1960s, people started again looking for how to use S-matrix to explain hadron interactions. And this was primarily, a lot of people contributed, but it was primarily championed by Geoffrey Chew. And there's a very, very nice paper. I would strongly encourage that you read it in 1964, which is called The Search of the S-matrix Axioms. The basic slogan for this program was you get rid of the quantum field. So you don't want to think in terms of the quantum field, you want to think in terms of the observables directly. And then it lay dormant for a long while. I mean, there were, of course, always intermediate results. But mainly the numerical part of the S-matrix bootstrap was initiated again by these gentlemen here, by Miguel, Joao, Jonathan, Balt, and Pedro. And a real application, I mean that which might interest your particle physics colleagues, was found in 2018, where they tried to bootstrap pion scattering. But I should tell you that this area is still being explored, and if this thing interests you, you should join the fun now, because it's not very well explored as yet. So I told you that the idea of the S-matrix was quite old. Lots of people contributed, including Landau, Geoffrey Chew, Stanley Mandelstam, Lehman, Martin, André Martin of the Froissart-Martin-Baum fame. And it uses very basic principles. And the basic principles are the Lorentz invariance, unitarity, and analyticity. And then you impose, and there somewhere there is crossing. Basically, crossing follows from analyticity. But you want to impose these crossing conditions, crossing symmetry. And the question that you want to ask is, are they constraining enough? And the pion scattering is a nice problem to study, because the analytic structure is kind of simpler. But to warn you, you really cannot make pions as external states and scatter them like what you can do in a proton. With protons, you really don't have a pion collider. But you can study these processes indirectly. I mean, pions were originally studied via cosmic rays and so on. But you can infer a lot about these processes. And the pion scattering process is one of the most considered processes for a lot of axiomatic QFT results. So the kind of thing that you can set yourself a target in acquiring, so imagine that you had your own way to solve these bootstrap equations, is to try and match up with this table here. So this is the table that is taken from this very famous review from 2001. It has, these are called scattering lengths and effective ranges. A's are scattering lengths, B's are called effective ranges. I'll flash a formula what these actually mean. But a target would be to reproduce this table. And the other thing that you would want to reproduce is this Regge behavior. So suppose you have solved it and you have your S matrix, then you can ask, does your S matrix exhibit this Regge behavior? And compared to the CFT story, you know that there is a CFT bootstrap. The CFT has a lot of extra symmetry. So there was the dilatation generator and the special conformal transformations. We don't have these, so we will need to work harder. And maybe we will need to put in more assumptions. And just again, this is a reminder that I wanted to remind you that the S-matrix story historically was developed earlier than the CFT bootstrap story. Although in the modern incarnation, it's just the opposite that has happened. And if you are a string theorist, why it should interest you is that you should remember that Regge plus crossing is what gave rise to gave birth to string theory. So this is just to go back and study scattering once again. So this is our favorite center of mass 2 to 2 scattering. You have M, the amplitude is a function of S and T. What you do is what is called a partial wave expansion. So this is what you do in standard quantum mechanics as well. And you do a partial wave expansion. These P's are the Legendre polynomials. We are in 4 dimensions. So appropriately, these are going to become Gegenbar polynomials in higher dimensions. And these are partial wave coefficients. And unitarity actually puts this constraint on these partial wave coefficients. And there's an analytic structure. So we are going to consider this kind of analytic structure where you have cuts corresponding to the intermediate particles going on threshold. So for example, you can have a 2-particle cut or a 3-particle cut and so on. This is the complex S-plane, and the whole idea of the analytic S-matrix is to start off by assuming something about the analytic structure of the amplitude and then analytically continue to various channels. And so, of course, this was a very famous book in the 1960s. And all of these are Cambridge men. So these are cuts corresponding to the thresholds, and you could also have bound states. So these would show up as poles. Now, for the pion scattering, you don't have these poles. You just have the cuts. So that is one of the simplicity that happens. So suppose you wanted to solve the crossing condition that M of ST was equal to M of TS. You write down both sides in terms of partial waves, and then you will immediately see what the problem is. The problem is that imagine that you had an S-channel pole on the left-hand side. Or you could also think of a cut that is visible on the left-hand side. On the right-hand side, these are polynomials. These are Legendre polynomials, so they are polynomials in S. So whether it's a pole or a cut, it's not going to be visible from the right-hand side. This is hard. So that is why you get, it's hard to actually, without actually summing over an infinite number of partial waves, it's hard to make progress. So this is an inspired second version of the crossing. What you need to do is use a different basis. You cannot use this as a basis to expand. You cannot use the Legendre polynomials. You have to do something else. So these gentlemen here propose to use a crossing symmetric basis. So this actually expands the amplitude in terms of some crossing symmetric objects. So these crossing symmetric objects are just some conformal transformation that takes you from the cut plane to the disk. So this is the transformation that does that. So here, as you can see, these variables rho s has this 2-particle cut visible. So this cut gets mapped to the boundary. And now you can start asking interesting questions here. So since we have used a crossing symmetric basis, the thing that you have to check is whether unitarity is being satisfied or not. And somewhat non-trivially, these conditions, so this is mod FL square, okay? Now, these are the parameters here, alpha, ABC, that you want to constrain. So these are just some basis elements. So there is nothing, no free parameter here. You fixed everything here. These are the free parameters. And in terms of the partial wave coefficients, these parameters, the partial wave coefficients would be linear in these parameters. So f of L, which is square, would be quadratic in these parameters. So quite remarkably and quite non-trivially, these quadratic constraints can be recast into what is called a semi-definite programming problem. And this semi-definite programming is what is largely inspired by the conformal bootstrap. And there are solvers which were written by various people. The one that we're going to use was written by Simmons-Duffin, which enables you to solve this problem. This is what these gentlemen also did. So the job is that you're going to use your constraint conditions and you're going to constrain these parameters. And pion is basically just a generalization of whatever I've discussed here. There is some global symmetry because there are 3 pions, pi 0, pi plus, and pi minus. There's some global symmetry there, some story there, which you have to incorporate, but it's basically straightforward. Now, as I said, that if you wanted to discuss this analytically, you would need to use chiral perturbation theory. And the state of the art for chiral perturbation theory is that one can go up to 2 loops, but because it's an effective field theory, you have to introduce a lot of phenomenological parameters when you do this. So it has been done by a lot of people, including my colleague Anant in the Center for Energy Physics. And the idea is that you want to do the bootstrap and you want to do it as a function of these Adler zeros. So the Adler zeros are basically zeros in certain partial waves of the chiral perturbation theory expansion. So these are zeros that are known to exist. I mean, there's a deeper reason why these zeros are there. It has to do with chiral symmetry breaking. It has to do with partially conserved axial currents. But basically, you can show this was done by Adler that these zeros must be there. But the thing to note is that these zeros are unphysical. Why are they unphysical? Because the physical region corresponds to S bigger than 4, and the zeros exist when, depending on which isospin you're considering, they are below 4. So they are unphysical. And as a result, you have to consider treating them as parameters and asking where your physical theory lives, because there is no a priori fundamental reason to say that these are the precise location for the Adler zeros. And they should exist also non-perturbatively, so they should exist also in this S-matrix bootstrap program. So what do we put in when we bootstrap? So we put in that there should be Adler zeros somewhere on the S0, S2 plane that corresponds to the vanishing of these partial wave coefficients. So the superscript here corresponds to which isospin I'm considering. As I said, pions correspond to various isospins. And so this gives us the Adler zero somewhere. And of course, you have to put in some more things. I mean, just putting in the fact that there are Adler zero somewhere is not going to be enough. We put in one phenomenological input, and that is that the rho resonance is somewhere on the we put in the value of the rho resonance. So the rho resonance takes on this value, so we're going to put that in. So that's the only phenomenological input. And then you can define what the scattering lengths and effective ranges are, and you can ask what these are from your bootstrap. And these are important because they are measurable experimentally or on a lattice. And that's why you make contact with experiments. So the where relative entropy comes in is that if you compute using this one loop chiral perturbation theory, then you will see that this dq, the quantum version of the relative entropy that we defined, takes on specific signs depending on which process you're considering. And these specific signs, you can either think of it as a feature that arises from relative entropy, but there is a fundamental origin behind these specific signs. It has to do with what is called the Frossard-Gribov representation of the scattering lengths. And these higher spin scattering lengths are known to, some combination of these higher spin scattering lengths are known to be positive. That's what gives rise to these signs. So either you think in terms of the relative entropy or you think in terms of this alternate of this Frossard-Gribov representation, you will be forced to consider these kind of signs. Okay, so what these gentlemen originally did was they found some allowed regions of S-matrices. So how did they do that? So basically, they looked at maximum values and minimum values of the S-matrices and looking for Adler zeros. So if the maximum and minimum take on the same signs, then obviously you cannot have a zero. So suppose your S matrix was had this as the maximum and this as the minimum, there is no zero. It doesn't intersect the x-axis. And what they found, or what they observed, was that there was a range of values. So this is, we are plotting S2 here, it should be S2 on the x-axis. There's a range of S2 values which are disallowed. So with this, you get what is called the lake. So you're doing this S0, S2 plot, and any point on the S0, S2 plane is allowed. Here it's an allowed theory, here it's an allowed theory, but the white is not allowed. What is excellent to note about this white region is that the leading order chiral perturbation theory, the tree level, not the one loop, the tree level actually lies in the disallowed region. And why is that? So should I be surprised? You should not be surprised, because we had input row resonance, and resonance is anything but, I mean, so the leading order, you can think of it as a free theory. And if you have a resonance, it's anything but free. So it's not surprising that this is ruled out. But you see, there is a lot of region which is still allowed, and you've only input the row resonance as your condition. So where is the standard model? Why should some region here be selected over anything else? So what you can do is you can take a step back and you can put in by hand what is known about the experimental scattering lengths. And because you've put this in, you will obviously get a smaller region. So the white is now disallowed. White in my convention is always a disallowed region. But what is interesting is that there's still quite a lot of S-matrices that are interesting that are left over. And all of these are compatible with the experimental SNP wave scattering lengths. And you see, so this is, in this sense, it's still interesting. So of course, you've taken a step back, you've put in some more experimental results in by hand, you've gotten a smaller region, but still there is still a lot of things that are left over. Now, we don't want to put in experimental things. We want to put in these relative entropy inequalities that we had. Then what do we get? So if you put in the row resonance and these signs, then you get a different region. It's not this smaller region which is dubbed the peninsula. So this region here was dubbed the peninsula. But you get a river. Now this is nice because you just put in one experimental information and some sign considerations. And what is also nice is that this one loop chiral perturbation theory, which does a reasonably good job to explain experiments, actually lies in a bend, a sharp bend. There's because of I mean, I don't know whether this bend is visible or not, but this one loop chiral perturbation theory actually lies close to what you would like to call a kink. So first of all, it's quite surprising that it lies on the boundary of the allowed region. So that's quite, in some sense, it's parallel to what was happening from the CFT story. The interesting theory, the three-dimensionalizing model or the O2 model actually lay at the kink, but also it was on the boundary of the allowed region. But again, there is a lot of freedom allowed. So for example, you can start asking questions like, can I distinguish this theory that is lying on the green from this theory which is lying here below? This is where, again, relative entropy can play a role. It will tell you how to distinguish these theories. So for example, you can ask, if I consider a theory that is living on the upper bank, how close is it to the one loop chiral perturbation theory? And if I consider this theory, which is lying on the lower bank, is it really far? Because physically it seems like it's very far, but is it really far from this one loop chiral perturbation theory? So these are the kind of questions that you would like to ask, and relative entropy is a great tool to enable you to address that. And as I said, you can do this hypothesis testing, and what you are going to find is that this entire green regions, depending on which reaction you're considering, these green regions are, in a very precise sense, very close to this red cross. In what sense? We are doing a low energy expansion, so we are expanding in powers of s minus 4m squared. So in that sense, if you consider a value of s that is close to 4, all these theories are actually equally close to this red cross. So then the question becomes, where is the standard model? So you can start putting in more ingredients. The one ingredient that you can start putting in to constrain the bootstrap is what is called positivity. And this is positivity in the extended Mandelstam region. So basically, one can use the Froissart-Gribov representation for the scattering lengths, and you can come up with very interesting positivity conditions. The basic statement of the positivity condition is that if you are anywhere inside this trapezium, or this quadrilateral that is there, then these derivatives have to be positive. And because you're in this region, the M actually is real, you're away from the cut. So this is real, so it makes sense to consider this as a real inequality. So you can impose these inequalities on the bootstrap and ask what you get. This is what you get. So originally, the river had a little bit more water in it. You just get a small shortening of the river, not much. The river is slightly narrower. And this makes it a little clearer that you can see that there's a sharp bend, and the one loop chiral perturbation theory is actually close to the sharp bend. So this leads us to the questions. I'm almost done, just 2 more slides. Why is the standard model special? What extra ingredients can we put in? And can we do something? Is it really true that the consistency conditions will allow us to get a small region that is surrounding the chiral perturbation theory result? Or is the answer more interesting? Could the answer be that the standard model actually lives here inside? It's not known. So, but at a primitive level, we would like to understand: is there really a kink? By that I mean that we have to make our numerics sharper, and then we would like to extract the spectrum of resonances to see whether we can distinguish these theories at the level of the spectrum as well or not. One thing that I did not put in, and of course, what is called elastic unitarity, which basically means that you cannot have particle production between 4 and 16 for a theory with Z2 symmetry. And this is something that is difficult to put in because it's a nonlinear constraint. But there are recent suggestions by Correa, Ametsevar, and Sasha Ziber of how to put this in. And it will be interesting to see what happens when you do this. So here are my immediate future wishes. Now, we have been doing this using very limited resources. Part of the reason is that some of these ideas that came to us happened during the time of COVID. So just to put things into perspective, people who do numerics for the CFT bootstrap have good resources. So this is basically the state of the art that they have. They have close to 49,000 CPU cores. And even the S-matrix attempts, which was done by Andrea, Joao, and Pedro, they used the PI cluster, which had around 2,400 cores. To put things into perspective, we put together some 50 cores of computing powers. We had 2 workstations that were generously enabled us by my wife, who's an experimental physicist. We had 1 node in 1 old cluster and then another in a heavily used cluster. So this is what is called Indian jugaad. Okay, this is something that Chinese people should learn. This word is called jugaad. So you actually want this Harley Davidson, a nice bike, but actually what you have clobbed together is this. So it's made up by boots. So it's a nice thing. We are doing bootstrap, but literally we have old boots and we've clobbed together some version of our Harley Davidson. But maybe just not to belittle ourselves. Because we have limited resources, maybe we will be forced to think in different ways, and here necessity will be the mother of invention as well. So there are more questions. I'll just leave this up for you to see, and I'm happy to discuss further, explain more things to you. Thank you.
Thank you very much. I really like your one slide back, the picture. Nice bootstrap. Any question?
Yeah, I'm sorry I had to rush through the S-matrix side, but if you wanted to know more, I'll be happy to explain.
So if you have a question, just unmute yourself. So then I have one questions. So in this parameter space, so you just show the region river, right? By using this this relative
Yes.
entropy.
Yes.
So it's one loop, but can you go farther, like 1, 2 loop and so on?
Yeah. So in the parameter space, the allowed region is of course not one loop. It's non-perturbative, so there is no expansion parameter.
Okay.
So this is just a point of comparison as to where the one loop ideal perturbation theory, which is the phenomenological side, where that lives, because this is supposed to describe experiments pretty well.
I see.
Okay. So this is non-perturbative. So any of this is consistent with whatever inequalities, whatever symmetries we have imposed so far. So that's the idea. So this is the one loop or two loop is just a point of comparison.
I see.
So any of this is an allowed S matrix in the sense that it satisfies all the constraints that we've imposed. Yeah.
Yes. Can you connect something to just CFT bootstrap, like?
Yeah, excellent question. Yes, in fact, I think it is possible. So because that is how you would do normally. So if you open Peskin and Schroeder, you would start off by doing the epsilon expansion. So you would start off with a massive 5/4 theory, and you would do the calculation. You would evaluate the beta function, and then you would solve the beta function, and you would look at the critical point. So if you bootstrap 5/4. Of course, you have to impose appropriate constraints. And you wanted to do this in, say, 3.99 dimensions. You want to do it in a fractional dimension. Then the critical theory is going to be somewhere in the allowed space of S matrices. And indeed, you could ask, how do you pinpoint the critical theory? I mean, imagine you did not have this notion of the beta function. What is the technology that you would use to pinpoint where the critical theory lies?
I see.
Yes.
Any other questions?
Yeah, Janet is asking questions on Skype. Janet, you should ask me here. Yeah.
Is she going to?
No, I think she has to leave. Yeah.
Because I have
she is.
And so
okay, so
very stupid paperwork, but I have more questions for you. I'm really sorry.
Yeah, okay, sure. Yeah, we'll catch you later.
Sorry about that.
So if there's no other question, let's thank Aninda for whatever method. Thank you very much. And then I will stop the recording.